Welcome to the Construction Brothers Podcast. I'm your host, Tyler Campbell, and with me, like he is every week, my brother, Eddie Campbell.
What's up, Tyler?
Not much, Eddie. Well, this week we are exploring traumatic brain injuries. Eddie, it's a Monday morning.
Yeah.
I feel like we just kind of rolled in here.
And you're going to roll in here and be like, let's talk.
Let's talk. We're
Traumatic
prepared.
brain injury.
We're prepared to have a very deep conversation about traumatic brain injuries this morning, for sure.
Why are you prepared for that, Tyler?
I've just a lot of coffee. That's how I'm prepared for it.
I got it. I just wanted to clarify.
But we have an expert here with us, Dr. Bottlang. How are you today?
Hi, Tyler and Eddie. I'm doing great. Thanks for having me. It's exciting.
So I heard you speak at an AGC event and heard your whole kind of presentation and stuff because you work with Wavecell, which we're familiar with, and we've seen a lot of photos and stuff of. So I saw you present, and it's just absolutely fascinating what you showed us. But let's dive in just really quick, kind of introduce yourself, tell us who you are and what you do, and then we'll kind of dive into the nuts and bolts of brain injuries here in a minute.
Oh, awesome. Yeah, Michael Bottlang, born and raised in Germany, was a researcher, scientist all my life. Actually, I had the pleasure to start a research lab in Portland, Oregon. It's non-profit, government supported. But one of the things we worked on for many years, like over 15 years, is brain injury prevention. And we also came up with something that we have data to show that it can really mitigate the risk and severity of brain injury, called Wavecell. And I'm super excited to talk about our new helmets for construction workers because that's where the most brain injuries happen. So this is where you can prevent the most.
So how did you get into this? Because you didn't actually start out with brain injuries, right? You were somewhere else.
That's absolutely true. I'm trained back in Germany even. It's all about broken bones and how to fix them with plates and screws. That's kind of home for me. That's where we made significant impacts. We developed, for example, a system when you crush your chest with many rib fractures. Something like that happened probably to Jeremy Reimer. Many surgeons around the world today use our rib plates, and after you fix those ribs, people can breathe again. So there was the opinion before, well, if you break your ribs, the lung is broken too. So a surgeon really didn't do much. But they quickly found out that the lung is like a sponge and it comes right back. It didn't break, but you need to restore the ribs so people can breathe in. Now that's something, it's a severe injury. The surgeon comes in, puts the plates on, and patients within weeks can do regular work again. It's phenomenal. Now, that's the opposite of what happens when you injure your brain because you get to the hospital and no surgeon can do anything other than relieving pressure. There's nothing you can stitch back together, and brain recovers function over time, but only partially and very slow. Often with limbs, like you break one leg, you can still get along in your life with the other one. Brain, we have one, and it affects everything we do. So once we recognize that, we feel passionate. There was another reason why we looked in brain injury. As researchers, we can't believe opinions. We always need to look at the data. And the data are stunning. They showed that the brain is injured by a rotational force. But then we look at the test standards for every helmet, from bicycle to construction to motorcycle, you name it. They're all tested straight down. And we only measure straight forces. So the actual mechanism that injures the brain is completely ignored. All the tests were done to look, when does a skull break? But we know that most brain injuries happen without a skull fracture. So anyway, as a researcher, complete disconnect between what the data show and what we actually do. And we thought like, hey, can we do better? And as researchers, we just can't help ourselves of getting into another 10-year endeavor.
I have an immediate question, and we describe a little bit more, like what's the difference between a rotational impact and maybe that like linear impact that you were talking
like
about?
The straight down forces.
Yeah, like what does that look like? What would be and maybe an example of a rotational impact?
So the straight impact is typically what you think of a hammer dropping on your head or you bumping into a wall. And there's actually a level where your skull starts cracking. They call that linear force or linear acceleration 300 G. Very straightforward. Now, the rotational force can get straight into the brain without the skull ever breaking. An example would be, look at your top-loading washing machine, stare right down. Nothing is really touching the laundry. That washing drum just rotates left, right, left, right. Whenever it reverses direction, reversal of acceleration is actually called jerk. It's an engineering term, so the laundry is being jerked around magically just by changing rotational acceleration. And that agitates the heck out of your laundry to make it clean. Unfortunately, that can happen to your brain. Now, when you think of our head and the fall that induces rotational acceleration, it's not that you see someone being spun. The most typical one is if you get hit on your chin as a boxer. That's the way to knock someone out, because your head will just rotate a little bit. And that little bit, if it happens quickly, that's the trick. That's the impulse that travels to your brain. It will literally distort your brain. And I will send you a nice video that you can post that shows a boxer being hit. When you watch it on TV, all you see is that boxer dropping and being knocked out cold. If you have slow motion to see the data, it looks super, I apologize, funny, because you see the teeth moving over 2 inches, but the lips stay where they were. So every child would laugh how funny that looks, but every grown-up, once you know what it does inside the brain, recognizes that the skull rotates and tears through the brain. That's why the boxer is knocked out. That's our prime vulnerability in the boxing ring, on the construction side. In fact, slips, trips, and falls are the #1 cause of brain injuries. All it takes me, ground level fall, hitting the concrete, it looks kind of straight down, but your neck will give it just that little rotational knock, and that can give you already a concussion.
I've seen the video that he's talking about too, and I'll say this, that if this is a perfect video to watch, so go to the YouTube version of this if you're listening on audio. We'll try to post some of these videos while we're talking so you can kind of see what he's talking about. Because, yeah, that video that you're talking about with the boxer, that was amazing. Yeah, you see their lips just over here on the side of their face and their teeth are over here. And, yeah, I don't – is that a concussion at that point? Like when you have that rotational force, at what point does a concussion occur? And kind of explain that for me.
Oh, there's a brain.
Hey, there's a brain.
That's a silicone brain. It's actually kind of heavy. 5 kilograms. It's considerable. And it's very intricate structures. And really the way the brain works in very simple terms, it's lots of neurons, brain cells, but they by themselves can't do anything. They need to be network connected. So you have millions and millions of very fine branches that connect the brain cells. If this thing starts getting twisted, and it literally gets twisted like that in the boxer, and then it yanks on the cables that connect the brain cells, and that gives you the permanent damage. So if you get knocked out cold, that's, and they call it diffuse axonal injury. So the axons are the cables that connect the brain cells. If a few get injured, torn apart, or yanked on, you might not see for a few seconds. That's a common thing. I just watched a ski race. My daughter was on the ski team. The one person falls, and the guy goes like, "Oh yeah, I couldn't see for like a half a minute." And it's like, "Oh my gosh, you were lucky. That was the onset. If it would have been a little bit more, it goes in stages, and you lose more and more of your cognitive function. Some might come back, some might not come back."
That's the thing, is it doesn't return, right? Like in most cases, like the brain can, I would assume, heal itself to a point, but for the most part, you're just kind of left in that state, right?
Yeah, well, the brain has to learn to reconnect. It can figure out where do we have still intact connections, and it needs to shift information. But that's a very slow, tedious process.
Unlike a broken bone.
Exactly, unlike a broken bone. If there would be a magic bullet that can prevent the brain from getting torn like that, that would be the #1 intervention.
Well, I think this is a good place to kind of show the egg video. I don't know about you, but I think this kind of demonstrates this point a little bit. And so, Eddie, I've seen this.
Yes.
So I'm going to let you view it, and we'll put it up again on the YouTube version so people can see this. And I would recommend you go watch it because it's eye-opening to see this rotational force in action, and then we can kind of get into it from there, right? So here's the video, Eddie. There you go. Don't drop my phone.
Yes, sir.
And Dr. Bottlang, if you want to kind of explain what's happening in the egg video and what this displays for us.
Oh, it's a fun story with the egg video. I'm a scientist studying computer models, and I showed that in a straight impact, brain doesn't deform. And people looked at the model and I got that blind stare. No one believed it. So Dr. Mady, my partner in research here, he said, make an egg video. And I refused to do it for a year, and I finally did it just to make that discussion go away. And it's super impactful because, yes, you see a head surrogate, like a fake head, coming down, but the weights are all proportional, the sizes are all right. And in the brain, we suspend basically, in a brain surrogate out of silicone, we suspend 2 raw egg yolks. And we hit it at high speed onto a hard surface. So everybody is expecting those egg yolks to either explode or jump up and down vigorously. And we see zero motion of those egg yolks because fluid is incompressible. That is basic physics. That's how the brain is protected. But if we take that same surrogate and we hit it with a slight rotational force, then there are rigorous shear forces that tore the egg yolks apart. And if we could build a helmet that prevent those egg yolks from being disrupted, then we would have a winner.
I think it's so fascinating to watch this is that, that direct force, that straight down force just does absolutely nothing to it. Like absolutely, and the egg yolks stay intact.
It jars it, but
It jars
it's not in a way that it's actually making it disintegrate.
It's making it rip,
yeah.
like making the yolk rip. And I thought that was it was an impactful way of showing it because it shows the yolk just basically just ripping apart in the video. And so I want to know, like, how often does a rotational force like this happen though? Like, do you have any statistics or anything to kind of share to say like, hey, this is more common than you might think on a job site or on an infrastructure project or whatever?
OSHA reported 54,272 cases of severe injury in a given year. And these are severe injuries. That doesn't mean the concussion where you feel nauseated, you want to go home, you have a headache, you should lay down. For example, in the ski team racing of my daughter, in one season, in one small team, we had 3 concussions. So these weren't severe brain injuries, but they were still concussions. And if you have multiple concussions, that doesn't bear well because they add up over time. And later in life, you just have those symptoms like I can't concentrate, I can't remember, I'm getting a little bit quicker agitated. Now that it might be me getting older, but it directly relates to those concussion events. So it really saddens me when I see younger people already getting into that. In the past, people always were laughing about, I just rang my bell. But today we really know better that ththese are additive events.
Well, go back to that 54,000. So of that 54,000, how many are we talking then?
Like, what is there a breakdown of slips, trips, and falls? I guess that would kind of fall into that.
Yes, over 60% are slips, trips, and falls. And also the majority of impacts happen to the front, side, and rear of the helmet. The fewest ones happen to the crown. And it's interesting when we talk about why use hard hats, there's that video with the watermelon that really shows if something is dropping on the top of your head, a helmet is doing a fantastic job. And helmets do a fantastic job. The cheapest hard hat is doing an incredible job in protecting anything penetrating your skull. I mean, problem solved, but for the brain, it's a completely different story. And also, where we get hit the most, it's a completely different story. It's not the crown of your head, it's the sides.
So go into some of what you've done with Wavecell to deal with that rotational problem.
The first thing is that Wavecell wasn't born as an idea, oh, we're smarter than others, that's how we do it. Wavecell was really born from many years of research and government funding. And step one is we made a tester where we now drop a head that has sensors in it that measure straight forces and rotational forces, and we drop it more realistic where we can impact the side or the front or the rear. And then we see those rotational forces. We see what happens without a helmet, what happens with a helmet. And then we tried many, many things. The first idea was, oh, let's just put a slippery liner in there, because then you would slip away from that rotational force. And we couldn't really get strong benefits from it because an impact event happens in milliseconds. You don't really see it. It happens that quick. So if it's a few milliseconds, the forces are crazy high. 10,000 Newton. I'm not making that up. That's actually a threshold that you need to stay below to pass, for example, an EN standard. 10,000 Newton is a ton, a weight of a small car. That's the magnitude of that impact force. And under that force, something slippery will not slip. It happens later when you recoil. So that's the first thing we learned in research, that our instant idea now, well, that didn't pay out. So we recognized we need something that can fold on itself. So even upon during 10,000 Newton force, as long as it folds over like kind of cards that are upside down and fall over, like the domino effect, that would work. So we thought like, hey, cool, let's use a regular honeycomb, yeah? Because honeycombs are three-dimensional, and if they could fold on themselves, that would be great. Unfortunately, the cross-section of a regular honeycomb tends to be kind of cylindrical, that's how they make them. And that's the shape of your light pole, like very strong against folding over. Like your drinking straw, it doesn't want to bend, yeah? Except you have the bendy straw, you know, the one with the wiggles in it, and now it wants to bend. Now, check out Wavecell. If you look carefully into each cell, they have this little bendy in it, in each cell, yeah? So now this, in a shear force, can actually fold over. So that was a key mechanism that we needed to design in. And all of a sudden, our forces went down, the rotational forces in our test model. It's like, wow, that's a winner. Of course, we also needed to make sure that the material can be put inside a helmet, because we also learned that you need like a whole dome to protect you all around. And that dome can't be made out of multiple pieces, because what Wavecell will do, it works like an accordion. So the whole liner can move and compress. It actually will probably move by an inch or two. So when we try to take a regular honeycomb in a helmet, when you bend it, it forms like a Pringle chip, like a horse saddle. So it doesn't want to go in a sphere. That's when everything collapses. Well, Wavecell is a crazy material because upon bending, it becomes a sphere, a dome. So we can make one big sheet that goes inside. So once in a helmet, Wavecell is a system that works by folding over, by crumpling like a crumple zone in a car, and then the whole liner can slide. And you will see in the video for yourself that this combined mechanism eases into the motion and protects the egg yolks from breaking.
That's the interesting thing about, like, we've got some old hard hats over there, like from the 60s, maybe 50s even. Yeah, the crumple zone is obviously not there, right? And we kind of talked about this before. It almost feels like some of the older hard hats or some of the like traditional, we'll say, with like the ratchet on the back, like the normal thing. It almost locks your head in place. So if it does get twisted, it would almost like make the rotational force worse, if that makes sense. I don't know if I'm making sense there, but it almost feels like it would grab your head and make it spin worse.
It makes total sense. You brought up two interesting points. The first one was what happened to hard hats. So this here is a 1967. That's exactly my vintage hard hat. Yeah. So inside you have that strap system, and this is a 2021 hard hat. Strap system, yeah?
They look about the same.
Yep.
No, here we have the innovation of the earmuff slot. That's the only real difference. But you have to say that this strap system is exceedingly effective against something from falling right on the crown. I show you why. Here we have a cross-section of a helmet. See, in this one here, you have a lot of airspace, so if something comes down, the helmet can deform, and the load is all being distributed. Super system. I mean, that's before World War I. That's what people used in helmets. It works. But if you have a side impact, look, there's nothing that is between you and the object other than a rigid shell. There's no damping, nothing. And that's where most of the impacts happen. So it's called a Type 2 helmet. There are Type 1 and Type 2. It's very simple. Type 1s are only tested from the top. That's it, passed. If you want to pass Type 2, you also get knocked from the side, and you need to dampen that impact. So to make a Type 2 helmet, all you need to do is put a sliver of styrofoam all around. And then they perform dramatically better for side impact. So I always recommend a helmet should be Type 2 rated. It's such a simple thing to achieve, and it's what we owe every construction worker. However, and now I come back, Tyler, to your point, those foam helmets, when we tested them, the Type 2 or climbing style helmets, they can hold your head much better in a sense. So if you hit the ground, you transmit actually higher rotational forces. So while it protects your skull better, it can actually be worse for your brain. So your ideal helmet should dampen the straight forces, and it should dampen the rotational forces, and that all the way around, not just at the crown. That's a simple requirement for a hard hat, and that's what we worked on, what, if I can show you, a Wavecell helmet will do, because, let me take out the liner here. What you see, it's a Wavecell dome that goes all the way to the edge where your traditional brim starts, and it's a one continuous liner, and no matter where you get hit, you have the linear crumple zone that works super efficient, but you can also mitigate that rotational force that's so dangerous for the brain.
That helmet style is becoming prevalent. And I think that the industry at large is recognizing the fact that side impact is something that we need to guard against as well.
You mean the climbing helmet style?
Like the climbing helmet style. I
was at Denver the other day, and like that's all everybody was wearing, which
Yes.
I was kind of happy to see. I was like, all right, you know, we're taking some considerations into place. We're not using like the traditional style hard hat, right? So sorry, I didn't.
Well, it's becoming a mandate.
It is,
as you have evidenced. Mm-hmm. And I saw that. I wore a Wavecell out on site the other day and kind of showed it to one of the guys, and he said, "Oh, well, I've got the climbing style. Yeah. This is what everybody's going to be using." And it's an interesting discussion about the technology. And so
that's okay. So the style of it is something that we talked about the other day. Why did you guys go with like the full brim style versus the climbing helmet? Because I think that's an interesting conversation.
Tyler and Eddie, 2 points that you bring up are phenomenal. So first, why did we integrate Wavecell into a traditional full brim style? Because Wavecell would go into any style helmet. In fact, we introduced it in bicycle with Trek, and they sold over 2 million helmets. So the style doesn't matter. But when we ask many workers, voice of customers it's called, the vast majority love their traditional hard hat. And when we want to do a better head protection, we want to make it that people like it, that it's cool, that it's light. So that's why we chose a traditional hard hat style with a huge difference. The traditional hard hat is actually about an inch taller. Because Wavecell is so efficient, we could keep it just a little bit shallower so there are less bumps. That's the only reason why we have a hard hat. But here comes the big thing as a scientist. There are so many things that are done out of a true and good intention, but sometimes they backfire. I see so many articles. We should move from hats to helmets, away from hard hats to the safer safety helmets. As a scientist, I read these articles and I say, okay, where's the data point? Why are they safer? And I cannot believe that I can read through pages and pages of wording without any evidence. So guess what I did? You guys have an idea?
I'm going to say researched.
Exactly. I bought a whole bunch of safety helmets from the major brands. And I bought a bunch of Type 2 hard hats. And I tested them front, side, back, exactly according to the ANSI standard. Which ones perform better, the safety helmets or the Type 2 hard hats? What do you think?
Probably the safety helmets. I don't. Or is it? There's the.
It's interesting.
Because the Type 2 and the safety helmets would be similar, right?
Oh,
no?
That is so incredible that you say that, because that's what most people believe. It's all the teaching that safety helmets are safer. The data were very clear. Every Type 2 hard hat passed Type 2. The impact forces were like way below 150 G. Every single safety helmet did not pass Type 2. They were over twice as high in general. So by putting your worker in a safety helmet, you put him at greater danger. It was just marketing. Sorry to say that clear, but I have the data and it's peer-reviewed, and these informations are available for everyone to read. So I think it was this great intention. Hey, hard hats have never changed. Let's take something from the climbing helmet side and make it better. But it turns out they are not better. Now they have foam in it. Why didn't they do? And by the way, then I looked inside the helmets. They were all Type 1 rated. So if you go to a construction site and look at someone's presumably safer helmet, turn it around. If it passed Type 2, the manufacturer 100% will put Type 2 in there. They only put Type 1 in there if it doesn't pass. And I don't want to overgeneralize. Right now, several companies already did or just start bringing out a Type 2 helmet. But that doesn't take away from the story that the industry totally pushed for safety helmets, climbing style safety helmets, claiming they're safer when the data didn't bear it out. Now, they do have a mandatory chin strap, and I think that's a good thing for working at heights. But now many hard hats can be had readily with a chin strap too. So that's not really a differentiator. And then, of course, the big elephant in the room is, how do those safety helmets with the foam inside perform in rotational impacts? Do they mitigate rotational forces or not? That's a whole nother ball game. Now, the one thing I was stunned is many of those safety helmets have a lot of foam also on the sides. Why didn't they meet the standard? Well, you need to flip one around and you will see that the foam is very thick on top for the Type 1 impact, and it gets very thin on the side, so you have that nice profile, and it ends up right around here. So it's thin and stops early, and that's why they just did not meet Type 2, many of them. I would always recommend to anybody buying a helmet, look inside. If it says Type 2, you have a certain level of safety. Style is just a matter of style. It has nothing to do with safety, unlike all those promotions. I just talked to the director of OSHA, and he was super happy to see the data and completely agreed.
Yeah.
Okay, jump in. Go.
Me first, please. One, I would like to tag in the show notes to the research, to what you've published. I think that would be really
fantastic,
amazing,
yeah.
so that people have hard evidence about what's being said and they can read it for themselves. We also are researchers here at Construction Brothers and performed a research project on one of the helmets. We dropped a sledgehammer on it in a highly scientific. It was mainly for, hey, let's do something zany for YouTube.
Let's have some fun.
It's interesting that what we chose to do was a linear impact from a hammer.
Yes.
From directly above.
Well, that's the most flashy thing too, and like even some of the tests that we saw, that I'll say at the AGC event, like it was from the top, straight down. We were dropping something straight down and saying, see, and that's fine, okay, great, but it seems like a quarter of the equation, if anything. Like the other 3/4 of this equation is really the damaging part.
Yeah.
Right? Like our hard hats are already doing a pretty decent job with keeping us from the drop on the top of the cranium. Sorry, I'm completely blanking on the proper term for it, Dr. Bottlang.
the good old drop on the cranium. That's the scientific
drop on the cranium.
Well, I think it's interesting. I think with the best of intentions, the industry is trying to change it, and maybe acknowledging your first point that here's a 1960s hard hat. Here's a 2020 hard hat. And look, they look very much, the same. And perhaps there's some innovation that could happen here. And there's an acknowledgement. We can go to a different type and solve some of that. But construction companies, I mean, we have to admit, want to be seen doing the right thing.
Well, yes.
And once you get the inertia of an idea out there where this safety guy at this major general contractor says, oh, we're doing this, then that safety guy at that general contractor's office or that CEO at that general contractor's office is going to want to be seen as doing equal to or greater than the other company when it comes to safety, because this is a big deal for us getting hired and for us performing work. This matters. And we want to be on the public record as doing as much or more. And
I think it's interesting though, because I mean, what you were saying, Dr. Bottlang, is not all safety helmets are created equally, right? Like, so it could look like a climbing style helmet, but the innards, I'll say, the interior of it is really where the money's at when it comes from a type 1 to a type 2. So don't get lost thinking that, oh, just because it looks like a climbing style, that it is actually type 2 and it will protect from some of these rotational forces. Am I hearing you right?
Well, that's side impact. That's not even rotational force.
Well, side impact, yeah.
Yeah.
I mean, the key here is that style is style and performance is performance. And they are actually, only because you have a safety style doesn't mean you're safer. But Eddie, I want to really repeat what you emphasized. I'm blown away by the willingness and desire of companies to keep their workers safest. I mean, the reason why there was this quick, dramatic change towards safety helmets, even despite some workers not liking them, shows me how eager the companies are to protect their workers. And to me, that is an incredible potential to prevent injuries, because people are willing to adapt to a better technology, but this effort needs to be guided by data. Otherwise, it's not going the right direction. And I do know that from orthopedics, there are so many ideas, so much teaching. And by the time you do research, you find, well, some ideas do work and many ideas actually do not work as anticipated. So these strong intentions with putting real efforts behind it need to be supported by simple research.
So I've got one more question for you, and then our final question, which is our megaphone. But I've heard complaints about the cost of some of these new hard hats, right? And I wanted to tee you up to maybe address that in a way too, because a lot of people are concerned, like, hey, we're going from a $12 hard hat to something that costs $150 or $100. Like, this is an expensive jump. Granted, like if we're looking at just the numbers, that is an expensive jump. So how do you kind of push back against that and get people to, think a little bit differently on this?
3 arguments. The first is this is all made in the US from stop to finish, high quality, and you pay a higher price. Reason number 2, how much is your brain worth? How much does one brain injury cost? How much is your insurance rate going up? Reason number 3, that's something I came recently up with. So I go to a car dealer to buy a brand new car for my daughter, and the car dealer goes like, hey, I give you a deal. I sell you that brand new car, $100 cheaper, but I don't have an airbag then. Or I make it another $100 cheaper and I take the safety belt out. I mean, that would be a crime. You should never do that. How can we give now a worker a helmet? We know that we can better prevent brain injury if we put something in that specifically targets rotational forces. But let's go for the cheaper helmet. Interestingly, from the safety officers in the industry, we get very little pushback once they see the egg video, and I really appreciate you posting that because it's educational.
I think it's, for me, it's just doing the right thing, right? Like, I mean, we could get into the insurance side of it and all of that, but at the other side, it's like, well, okay, think of that as your daughter, your son out on a job site. You need to do unto others in a situation like this and give them the best shot of going home safely. Yeah, okay, something may not happen. And praise God if it doesn't, right? Like, that's great. I'm happy that we have a safe enough site that nothing happened. But the thing that really grinds my gears is when we get into just the ones and zeros of this whole thing. And it's just, oh, this is just too expensive.
Yeah. Which one would you rather wear?
The one that actually protects me personally. I mean,
ask yourself that question. Which one would you rather have on your head? The one that is more likely to keep you safe, or the one that's less likely?
Right. Yeah. I mean, and I thought of this the other day, Dad, after our little, AGC meetup, Dad had lost 3 guys on a job site. And if you ask him now, if there was something that was an extra $100 for each of those people, or if it was, $40,000 to outfit all of your people with this one thing that would have protected them in that circumstance, would you have done it? I know full stop he would have. Mm-hmm. Like, you do not want to look back and say, I wish I had. That's not a good place to live. So do everything you possibly can to prevent that. Give your people the best shot of going home to their families at the end of the day. There's my rant, right?
Actually, I can keep ranting on, because my main motivation here is I have a little poster wall out here, and every couple of weeks I get an email or I see a post on the internet where someone of those 2 million mountain bike and bicycle riders that use Wavecell, they crash. And they actually post or send me something. And these are sometimes from the hospital. I broke my collarbone and whatnot in the hospital, huge rashes, but no concussion, or just a very mild one. And they're so happy they had that Wavecell bicycle helmet. So Wavecell on the construction side, we're barely a year on the market, but that makes me super happy. That's why we do what we do.
That's awesome. I love it. Well, all right. So here's our final question for you, which is our megaphone question. All right. So, and we ask everybody this, and we love it. So if we give you a megaphone for the entire industry to hear, and around 60 seconds, what would you want to preach to the construction industry? What would you want to say? What would you want to leave them with?
Question what no one else questions. Don't just assume. Don't go by the style of a helmet. Ask how they are tested, what standard do they actually meet, and then go one step further and watch the ag video to recognize what causes the most concussions and brain injuries. It's the rotational force. And then look at what helmet can best prevent that. We don't want workers suffer from concussions. This is not something that in the past we could laugh about or were even proud of. Hey, I had one and I went right back to work. This is a serious complication that can affect the rest of your life. You do want to prevent as much as you can do it. And thankfully today there are technologies like Wavecell that can better protect your brain from getting a concussion.
This is good stuff. This is a really fun one, and it's very enlightening to come through and actually hear about the science and everything behind traumatic brain injuries. So, Dr. Bottlang, thank you so much for joining us this week. It was a pleasure.
My pleasure. Thank you for having me, Eddie and Tyler.